Hi everyone, this is Rumana Khanfar from Taqarub International Schools. This lesson is about compound body problems, or when we have two or more objects moving with the same acceleration. Like when we have two blocks hanging from the ceiling by a string or rope up and another one down. Or when you push or pull two masses or blocks on a surface with one force. After that, we will study the problems of two masses over a pulley and a different configuration when one mass is hanging freely and the other one is sliding over a surface. For all of the previous cases, we will apply Newton's law of motion, sigma F equals ma, but here m is the sum of all the masses which are moving at the same acceleration. So m is m1 plus m2 plus all the masses that we have, but mostly on the SAT test we have just two masses times the acceleration. This is sigma F. The direction of the net force is same as the direction of the acceleration, and this is sigma F of the whole system. Let's start with studying this case, when two masses are pushed by an external force over a surface. Firstly, to find the acceleration of this system. The acceleration of mass 1 or mass 2 is the same, so to find the acceleration of any of the masses, we apply this formula. Sigma F of the system equals m1 plus m2 times the acceleration. The acceleration for both is the same. A second thing you might be asked to find is the force between the masses, the contact force between the masses. If I apply a force of 20 newtons to move these two blocks, I apply the force on the first mass. As a result, the second mass moves because this mass, the first one, applies a force, a contact force on the other one. And as a response, because for every action there is an opposite reaction, mass 2 applies a force on mass 1. Equal and opposite. So when we find sigma F of the whole system, these two forces cancel out. If we need to find this force, let's call it F12, the force from mass 1 on 2, and this is F21, the force from mass 2 on 1. As we said, F12 equals F21, but they are opposite in direction. To find this force, we construct the free body diagram for one of the two blocks. And to construct the free body diagram, we draw all the forces from the center and out of the object. So this is the external force, F, and here this is F21, it is to the left. Now I apply the same formula, sigma F equals ma, the acceleration that we found previously in the previous step. Here on the second mass, there is one force acting on this mass, which is F12, the force from mass 1 on 2. And again, we apply the same formula, sigma F equals ma. We will get the same answer because here the mass is different, so the force will be different, although they have the same acceleration. Let's understand by applying these formulas on the next example. A force of 18 newtons pushes two masses. M1 is 2 kilograms and M2 is 4 kilograms horizontally to the right. Determine the acceleration of mass 2. As we discussed before, the acceleration of mass 1 and mass 2 is equal. So to find the acceleration, we use the first formula. Sigma F equals the total mass, 2 plus 4, times A. Here the friction is not mentioned, so we assume that the surface is smooth. The total force is 18 newtons. This is the only force that we have in the direction of motion. It's 18. 18 equals 6 times A. So A is 3 meters per second squared. Now let's go to B. Determine the magnitude of the force between the masses. The force between the masses is the contact force. To find it, we need to construct the free body diagram for each of the masses. Or for one of them is enough, but we will do it for both to make sure that our answer is correct. On the first mass, this is 18 to the right, and this is the force from mass 2. Let's call it F2-1, because mass 2 pushes mass 1 and mass 1 pushes mass 2. Okay, sigma F equals MA. Sigma F is 18 minus the force that we want, F2-1. This is equal to the mass 2 times the acceleration 3, which is the same for both of the masses. 18 minus F2-1 equals 6. Let's move this one here and this one there to the other side. So 18 minus 6 equals F2-1. Then F2-1 equals 12 newtons. Let's check our solution by finding the force for mass 2. Now, for mass 2, we have just one force to the right, F1 on 2. Sigma F equals MA. Sigma F is the force, the unknown. The mass is 4, and the acceleration is 3 again. So this is 12 newtons. We got the same answer because the force is equal and opposite to that one. Now let's study this case when we have two masses hanging from the ceiling and being held by two strings or ropes. For mass 2, we have Fg, the force of gravity or the weight. Up we have the tension in the string, let's call it T2 because it's connected with mass 2. And here, on mass 1, we have the weight down, and also we have another force, the tension here, in this part of the string. So we have two forces in the same direction, and it's again T2, and we have T1 upward because of the string here. This is T1. If this system is stationary, or if the two masses are kept at rest, the weight here of this mass is equal to T2. The weight plus T2 is equal to T1 for the system to be in equilibrium. Now let's solve this example. If the masses in the figure are kept stationary by two ropes, calculate the tension in each of the ropes. Let's start with mass 2. For mass 2, we have the weight down, or the force of gravity. We have the tension up, and we will call it T2 because this string is connected with mass 2. For mass 1, we have the weight down, the tension up, T1, and also we have T2 down. If the whole system is stationary or at static equilibrium or at rest, then sigma F equals 0 on both of the masses. Sigma F on mass 2 is T2 minus weight. This is equal to 0. T2 equals the weight. The weight of this mass is m times gravity, which is 10. This is 10 times 10, or 100 newtons. Let's go back to M1. For M1 also, sigma F equals 0. So T1 minus both of these, T2 plus the weight, is 0. T1 is unknown, minus T2, which is 100, plus the weight of mass 1. Weight of mass 1 is 5 times 10, or 50 newtons. This is 50, and it's all equal to 0. Then T1 equals 150 newtons. Of course, T1 is more than T2 because the string here holds 2 masses, while the string down holds 1 mass. Pulley problems. We have 2 main configurations on the SAT test. The first one is the Atwood machine. Actually, it is called Atwood machine because Atwood used it to find the acceleration of some objects. When we have 2 masses sliding over a pulley, we assume that the pulley is massless and frictionless. So we don't consider the weight of the pulley or the friction between the string and the pulley. To find the acceleration or the tension, we need to draw the free body diagram. Here we have weight 1, here weight 2. We have T2 and T1, or you can just simply call them T and T because it is the same string. Now, how can we tell which direction is positive and which direction is negative? If M2 here is heavier than M1, the system will move clockwise. So, the clockwise direction is the positive and the counterclockwise direction is the negative. This force is in the same direction of motion, so it is positive. Here, tension opposes motion, so it is negative. This tension is with the motion, so it is positive. The weight here is opposite to the motion, so it is negative. So sigma F equals M1 plus M2 times A. Sigma F, or the sum of the forces, is weight 2, positive, minus T, plus T minus weight 1, and this is equal to M1 plus M2 times A. And these forces cancel out because they are equal. In the next examples, we will understand more how to apply this formula. Now, let's go to the modified Atwood machine, when one of the masses is hanging freely and the other one is sliding over a surface. If the surface is rough, we need to consider the friction. This is the tension to the right. And again, it's the same tension here, and this is the weight down. If the system is moving in this direction, this is positive, this is negative, positive, and negative. Now, what if the system is moving in this direction? If this mass is being pulled by a force, the friction will be to the right, and the tension is also to the right. We have the same tension here, and this is weight of mass 2. If the system is moving counterclockwise, this is positive, negative, negative, positive, and this is negative. Actually, the weight of mass 1 and the normal force of mass 1 are not in the same direction of motion. We might need to find the normal force in order to calculate the friction. It depends on the case we have. Masses M and 2M are connected by a string, which is draped over a pulley. The masses are released from rest, so they will move according to their weights. Determine the acceleration of mass M. Then we need to determine the magnitude of the force of tension in the string between the masses. To find the acceleration, we need to construct the free body diagram of the whole system. We have weight 2 down, here weight 1, up we have the tension, and here we have the same tension. Because this mass is heavier, the system will move clockwise. So this is positive, negative, positive, negative. Sigma F of the system is equal to M plus 2M or 3M times the acceleration. Sigma F is weight 2 minus T plus T minus weight 1, and this is equal to 3M times A. These two tensions cancel out because they are equal. weight 2 is 2m times 10, 20m, minus weight 1 is m times 10, which is 10m. This is equal to 3ma. 20m minus 10m is 10m. This is equal to 3ma. M is cancelled out, so acceleration is 10 over 3 meters per second. Now let's find the magnitude of the force of tension in the string between the masses. To find the force of tension, we need to take any of the masses. Let's say the mass M. We have negative weight 1, positive tension. Sigma F equals M times A. Sigma F is T minus weight 1, and this is equal to the mass M times the acceleration 10 over 3. The tension is unknown. Weight 1 is 10m. This is equal to 10m over 3. Let's move this one to the other side. T equals 10m over 3 plus 10m. This is 10m plus 30m, 40m over 3. Of course, it will be easier if we have numbers, not symbols, but you need to study all the cases. And if we use the other mass, the mass 2m, we get the same answer. Another example about the modified Atwood machine. Two masses, m1, 2 kilograms, this is 2 kilograms, and m2, 3 kilograms, are connected by a string, which is draped over a pulley as shown below. Mass 1 is positioned on a horizontal surface, while mass 2 hangs freely. The masses are released from rest, so they will move according to their weights. Because this mass is heavier, the system will move clockwise. Determine the acceleration of mass 2, which is the acceleration of the whole system. Sigma F equals m1 plus m2 times A. Weight 2, 30 newtons. The tension here, the same tension. And the friction is not mentioned, so we assume that it has 0. We have the force of gravity, or the weight of this object, and the normal force. Actually, we're not going to use them here because they are not in the same direction of motion. Positive 30, negative t, positive t, and this is 0 here. So sigma F is 30 minus t plus t, and this is equal to 2 plus 3, 5 kilograms times A. 30 equals 5A over 5 over 5. A equals 6 meters per second squared. B. Determine the tension in the string. We can use any of the masses to find the tension in the string. Let's use mass 1. On mass 1, we have the tension. Friction is 0, so we're not going to consider it. And we're not going to consider these two forces because they are not in the direction of motion. This is positive. Sigma F equals m times A. The mass is 2, the acceleration is 6, so the tension is 12 newtons. Let's try to find it using this mass here, using m2. On m2 we have 30 and t. Sigma F equals ma. Sigma F is 30 minus t. This is 3 times 6. 30 minus t equals 18. 30 minus 18 equals t, so t is 12 newtons again. This is enough for today. If you have any difficulties regarding the previous cases, please let me know. In the next video, we will study the dynamics of circular motion. See you next time.